So in this video we will be seeing the remaining. So till channel coding we had seen. So in a channel coding, continuation of the channel coding, we are going to have the interleaver. That is, between two constant encoders we are going to have an interleaver. So what is the function of the interleaver is, whatever is going to be the input bits, that input bits are going to be directly sent to the first channel encoder, and that interleaver is going to scramble the bits and it is going to send the bits in reverse in some other order, that is going to the second channel encoder there, and the signals are going to be modulated. Output of this encoders are going to be modulated signal there. So here there are different types of interleavers. So interleavers are going to be pseudo-random interleaver, interblock permutation interleaver, regular permutation interleaver, quadratic permutation polynomial interleaver. So in our turbo encoder we are going to use quadratic permutation polynomial interleaver there, where it is going to have a good performance, low computational complexity and free parallel decoding there. And the last advantage is iterative decoding is used at the receiver decode turbo codes. So here the encoder what we are going to use, the turbo encoder, it is going to be a systematic one and a recursive one. And the interleaver is going to be a contention free interleaver. It is going to be based on your quadrature permutation polynomial, and because of the small parameter storage there. So because of this advantage, we are going to go for a quadratic permutation polynomial interleaver. Because of good performance, low complexity, computational complexity, free parallel coding and small parameter storage there. And output of this is going to be given to a rate matching and your physical layer hybrid ARQ functionality. So what it is going to do is, your rate matching is, it is going to create an output bit stream with a desired code rate. So with whatever code rate I want to transmit the data, this rate matching is going to provide an output bit stream with the desired code rate within the given total transmission time. So here it is going to depend on the available resources. So here basically if you see in LTE, your transmission of the data is going to be dependent on the channel resources available there, and based on the channel quality information, your resource scheduling is going to be done. So based on those, it is going to be provided, this rate matching is going to provide an output bit stream there. So here the input bits which are going to be given is going to be your systematic bits, first parity bits and your second parity bits. The modulated signal is going to be divided into three blocks. One is a systematic bits, the second one is going to be a first parity bit, and third one is going to be a second parity bits. And these are going to be sent to these bits are going to be sent to your subblock interleaver. So in a subblock interleaver, it is going to be interleaved. The bits are going to be interleaved and it is going to be given to a bit collection block, where a bit collection block is going to consist of a circular buffer. The output of this bit collection block is nothing but a circular buffer, a virtual circular buffer, where it is going to start from the systematic bits followed by one systematic bit followed by one first parity bit and second parity bit, then first parity bit, second parity bit. So here in this case it is going to be alternate between your first parity bit. First bit will be your systematic bits, followed by then your first parity bit, second parity bit, in an alternate fashion. These bits will be transmitted there in the circular buffer. Once it comes to the end of the buffer, again this data bits will be repeated there. So for this we are going to have, it is going to be, the parity bits are going to be indicated by your redundancy version, that is your RV. So here RV is equivalent to 0, that means that the first is going to start here. Then that once the circular buffer data are going to be sent, the bits are going to be collected, it is going to be sent to your bit selection. So a bit selection is going to be done based on the RV bit, and we are going to get an output bit stream with the desired code rate is going to be got. So the L bits are going to be read from the virtual circular buffer, and from one hybrid ARQ to next, L bits are going to be the same. So that is, your hybrid ARQ is going to check whether there is going to be any error in the received data. If they are based on that, we are going to do the data, whether the retransmission of data should be done or not. So in that case, one HARQ should be, the one HARQ and the other HARQ should, the length of the bit should be same. From the circular buffer, whatever we are going to read, the length of the bit should be same. but the parity bits can be different. So when the parity bits are going to be different, that parity bits are going to be based on the redundancy version what we are going to use there. So the code blocks at the output is going to be concatenated and it is going to have a code word input there. Next is your bit level scrambling. So bit level scrambling is nothing but in the interlevel when you are going to get it is going to multiply the code bits which is going to be delivered by the hybrid ARQ functionality by a bit level scrambler. That is, from the rate matching block and the hybrid ARQ block, they are going to get the code bits, and these code bits are going to be multiplied by the bit level scrambling sequence, which is going to be created using a length of 31 goal sequence generator. So we are going to have a goal sequence generator which is going to be of length 31, and using this length the bits are going to be scrambled and then it is going to be sent to the receiver side. So the receiver side decoding can fully utilize the processing gain provided by the channel code. So why we are doing it is to utilize the fully receiver gain, we are going to do the scrambling method here. So from your wideband CDMA or your high-speed packet access and the 3G also, the chip level scrambling is necessary so that the processing gain can be improved. So by spreading and it can be efficiently utilized there. So bit level scrambling, why we are going to go in for LTE is because of the lower implementation complexity and with no negative impact on the performance of the LTE performance in case of LTE there. So in LTE bit level scrambling, and in 3G it is going to be chip level scrambling there. Mainly why we go for a scrambling purposes is to increase the processing gain. We are going to go for scrambling process. Next is bit level scrambling itself. Your LTE downlink scrambling is applied to all the transport channels. So the scrambling is going to be applied to all the transport channels. The scrambling sequences are going to be your cell specific scrambling. So this why we are going to go for a cell specific scrambling is to ensure the intercell interference rejection, mainly to that is by getting the processing gain to be improved, you are going to eliminate the intercell interference there. So the scrambling depends on the physical layer cell identity there. In case of if it is going to be a multi-broadcast single frequency network based transmission, it uses the multicast channel transport channel there. So where we use cell common scrambling there. So this scrambling is going to depend on the so-called multi-broadcast single frequency network area identity. Next is your data modulation. So once the scramble bits are going to be got, it is going to be modulation is going to be done. So the downlink data modulation is going to transform the blocks of the scrambled bits into a corresponding block of complex modulation symbols there. So here the modulation schemes that are going to be supported for your LTE downlink is going to be a QPSK or 16 quadrature amplitude modulation or 64 quadrature amplitude modulation there. So all these modulation schemes are going to be applicable to the downlink shared channel coding, or it is going to be the physical channel and a multicast transport channel there. So the data modulation, the scrambled bits are going to be modulated and it is going to be transformed into a complex modulation symbols there. So the modulation schemes which are going to be supported is going to be a QPSK, 16-bit QAM and 64-bit QAM there. These modulation schemes are going to be applicable to your downlink shared channel, your physical channel and your multicast channel there, transport channels. And next is your antenna mapping. So antenna mapping is whatever data we have got, the modulated symbols, that modulated symbol should be sent. So for sending it, we are going to use your antenna mapping, where antenna mapping is going to consist of 4 antenna ports. So it is going to consist of 4 antenna ports. It is going to process the modulation symbols of 2 transport blocks. So 2 transport blocks is it maps the resultant results to your 2 different antenna ports. The antenna mapping can be configured in different ways to different multi-antenna schemes, including transmit diversity and spatial multiplexing. So the antenna mapping, it can be done in different ways. It can be configured in different ways based on the port or based on what is the type of transmission we want to do, and it is going to be different multi-antenna schemes are going to be for including your transmit diversity and spatial multiplexing. And next is your resource block mapping. So resource block mapping is the OFDMA symbols what we are going to get is going to be transmitted for each antenna port to the resource element of the set of resource blocks for transmission of the transport blocks to the terminal there. So here what it is going to do is, whatever symbols we have got, the OFDMA symbols we have got, it is going to be transmitted using the antenna port to the resource elements of the set of the resource blocks for transmission to the terminal there. So each resource block consists of 84 resource elements, that is 12 subcarriers and 7 OFDMA slots, that is OFDMA symbols. So here in this case 12 into 7, 84 resource elements you are going to have. Your resource block is going to consist of. The set of resource elements are going to be referred to as physical downlink shared channel. Next is your physical downlink shared channel. So this physical downlink shared channel may use a time or frequency domain scheduling. So here it is going to decide what set of resource blocks are going to be used for transmission to a specific terminal, and considering the channel conditions in both time and frequency domain. So here a physical downlink shared channel may be used in time or frequency domain scheduling there. So here in this case it will decide, a physical downlink shall decide what set of resource blocks are going to be used for transmission to a specific terminal, considering that it is based on the channel conditions in both time and frequency domain. So by doing this, it is going to improve the system performance. So in system performances, it is going to provide a high data rate and overall cell throughput there. Thank you.